there is a moment, a rather famous one etched into the history of science. It's the year 1919, and the world is still reeling, trying to find its feet after a war of unimaginable scale. But in the quiet, methodical world of physics, something profound is about to happen. Sir Arthur Eddington, one of the great astrophysicists of his day, has set off on expeditions to the distant shores of Brazil and the serene island of Precipice. His mission, well, it's nothing less than to put the universe itself to the test. He's there to observe a total solar eclipse, and in those fleeting moments of midday darkness, he hopes to measure the subtle bending of starlight from distant stars as it grazes the colossal gravitational field of our Sun. He's looking for evidence to support, or perhaps to shatter, a radical new idea about gravity, space and time, proposed by a German patent clerk turned physicist named Albert Einstein, his general theory of relativity. Now, this wasn't just some academic squabble. This was a direct question posed to the cosmos. Is space an empty, passive stage on which events unfold, as Newton had imagined for centuries? Or is it a dynamic, flexible fabric, warped and curved by the presence of matter and energy? Einstein's theory predicted the latter, and it made a very specific, quantifiable prediction about just how much that starlight should be deflected. The scientific community, was holding its breath. The stakes were immense. And in the midst of this anticipation, a journalist, sensing the historical gravity of the moment, approached Einstein. He asked him a simple, yet rather mischievous question. He asked, "What would you do, Professor, if Eddington's observations don't match your predictions?" And Einstein's response, well, it's one of the most sublime and, on the surface, perhaps one of the most arrogant statements in the history of thought. He said, with a quiet confidence that still echoes, "Then I would feel sorry for the dear Lord, for the theory is correct anyway." Now, you could be forgiven for perceiving that as a breathtaking display of hubris. You might imagine a scientist so deeply invested, so emotionally entangled in his own creation, after years of relentless intellectual struggle, that he simply cannot entertain the possibility of its failure. And of course, there would be a human element to that. But to read it only as personal pride is to miss the profound depth of what he was actually saying. Einstein's confidence wasn't rooted in ego. It was rooted in something else, something far more fundamental. His theory possessed a quality, an internal coherence, an elegance so profound that for him, and for many of his peers, it felt true long before the evidence came in. It had a kind of aesthetic perfection, a sublime beauty that seemed to resonate with the very structure of the universe itself. He couldn't imagine a cosmos that wasn't built this way, because any other way would be, it would be ugly. And as history records the universe obliged. Eddington's measurements, relayed by telegraph across the globe, confirmed that starlight did indeed bend precisely as Einstein's beautiful equations had foretold. Space-time was a dynamic fabric. The theory was correct. And in science, as in so many things, the victors aren't often questioned too closely about their methods or their motivations, but that statement of Einstein's, that quiet assertion that pure thought, guided by a sense of beauty, could somehow unveil the deepest secrets of nature, that's an idea that, once you've heard it, it doesn't quite leave you. It suggests a deep, almost mystical harmony between the machinery of the human mind and the machinery of the cosmos. I find myself profoundly convinced that this is the case, that through the patient construction of abstract ideas, through the weaving of purely intellectual concepts, we can stumble upon the fundamental principles and the intricate lawful connections that provide the key to understanding the grand pageant of natural phenomena. In a very real sense, it's an echo of a belief held by the ancients, that pure, unadulterated thought, free from the immediate constraints of what we can touch and measure, is capable of grasping the essence of reality. It's a profound declaration of faith in the logical architecture of the universe and in our mind's ability to mirror that same deep logic. Let me ask you to consider a phrase. It's a phrase that's almost certainly lurking somewhere in the neural pathways of everyone listening. For many, it might evoke a faint ghostly sensation of classroom dread, a mild nausea from a long-forgotten mathematics lesson. It goes something like this. In a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. Now for some, those words alone might trigger a kind of intellectual allergy, a desire to switch off. Others might struggle to recall precisely what it means, and I can completely understand if a few of you have already decided this isn't for you. But for its discoverer, the ancient Greek thinker Pythagoras, this wasn't just some dry geometric fact. Its revelation was for him a moment of pure religious ecstasy. The shock of discovery, the intellectual thrill of grasping a truth so elegant, so fundamental, and so undeniably true, was so overwhelming that it famously caused him to violate his own deeply held vegetarian principles. The story goes that in a fit of joyous gratitude to the gods, he ordered the sacrifice of 100 oxen, followed by a magnificent feast to celebrate this single, perfect moment of insight. All of that uproar, all of that profound celebration, was for the simple yet breathtaking realization that if you construct a square on each side of a right-angled triangle, the areas of the two smaller squares will always, precisely and without exception, add up to the area of the largest one. It's a harmony, a numerical relationship hidden in plain sight within the geometry of the world. And if you'd been there to perceive this truth alongside Pythagoras, you would have grasped something extraordinary about the universe. For some deep, inexplicable reason, the world of forms, the geometry of the things we encounter, embodies hidden numerical truths. It's not chaos. There's an order, an architecture, just waiting for a prepared mind to decipher it. But why should the universe care about our numbers? Why should its fundamental structure resonate with the abstract constructions of the human mind? That is a question that sits at the very heart of our quest for knowledge. The Nobel laureate in physics, Frank Wilczek, poses a question in his book, A Beautiful Question, Finding Nature's Deep Design. It's a question that might at first seem a bit strange for a hard-nosed physicist to ask. Is the world a work of art? Now, if you're working within a spiritual or religious framework, that's perhaps the most natural question imaginable. If a creator or creators brought the universe into being, it's entirely plausible that their motivation was simply to create something beautiful. And at the end of his profound exploration, Wilczek gives his own unequivocal answer. Yes, it is. The great existential psychologist Irvin Yalom identified meaninglessness as one of the four great anxieties of the human condition, alongside our fear of death, our isolation, and the terrifying burden of freedom. It seems that this relentless quest for meaning is what drives us not only towards religion, but also into the abstract and rigorous world of science. And in that quest, beauty acts as a powerful guide. It provides a sense of purpose, a framework that seems to suggest that the universe isn't just a cold, indifferent accident, but a place of intricate and coherent design. But this allure of beauty has a darker side. It can be a siren's call. It can lead scientists to perceive what they wish to be true, rather than what is actually there. This powerful bias towards the aesthetically pleasing can blind us to the harsh and often messy truths revealed by experiment. And according to the German theoretical physicist Sabine Hossenfelder, this very bias is one of the main reasons why her field, theoretical physics, has been in a state of stagnation for more than 4 decades, with a troubling lack of major breakthroughs. She lays out this provocative argument in her own book, which in English is titled Lost in Math: How Beauty Leads Physics Astray. One can't help but sense a deliberate provocation in that title. Wilczek's book, as I mentioned, is The Beautiful Question. Hossenfelder's is Lost in Math. It's a direct challenge, a gauntlet thrown down not just to Wilczek, but to a huge number of theoretical physicists who hold the deep-seated belief that a beautiful theory is almost always a correct one. And the number of people, both inside and outside of science, who subscribe to that idea is, well, it's astonishingly large. The scale of this issue, the depth of this conviction, is probably difficult for many of us to truly appreciate. Hossenfelder's book is a challenging read, I must admit, especially for an enthusiast like myself. Much of the technical detail was, I'm afraid, beyond my full grasp, But her central idea, her core argument, is remarkably clear and accessible. And her satirical, often biting commentary on her own colleagues is an art form in itself. It's no surprise the book became a bestseller, translated into at least 10 languages. Lost in Math exposed a deeply serious and peculiar problem, one that, according to Hossenfelder, few in the scientific community had really stopped to think about. Consider the timescales of discovery. It took 25 years from the prediction of the neutrino to its experimental detection. It took nearly half a century to finally glimpse the Higgs boson, and it took a full century before we could directly perceive the gravitational waves that Einstein had predicted. Those gentle ripples in the fabric of space-time, these are not trivial lengths of time. The unsettling reality that is now dawning on theoretical physics is that the time it might take to experimentally verify a genuinely new and fundamental law of nature could very well exceed the entire lifespan of a single scientist. And this daunting prospect, Hossenfelder argues, has led some theorists down a path of, well, a path of something bordering on intellectual desperation. The sensation of beauty in a physical theory, she argues, isn't just a fleeting appreciation. It seems to be wired into the very architecture of our brains. It's not some arbitrary cultural preference. When we encounter a theory of exquisite elegance, there's a deep, almost primal emotional response. It's an experience akin to standing before a great work of art, a feeling that goes beyond mere intellectual comprehension. Gianfrancesco Giudici, a brilliant Italian theoretical physicist at CERN, has reviewed a multitude of definitions for beauty, and he concludes quite candidly that we are, in essence, without a clue as to what it truly is. But, he adds, we absolutely cannot mistake it for anything else. Beauty, it seems, is unmistakable even if it is indefinable. But that raises a fundamental, almost philosophical question. Why should certain mathematical laws that govern the cosmos elicit feelings of pleasure in us? I mean, on the surface, it makes no sense at all. We are biological creatures, shaped by the relentless pressures of evolution. As the great geneticist Theodosius Dobzhansky famously said, nothing in biology makes sense except in the light of evolution. So why on earth should we perceive an abstract theorem or a speculative hypothesis as beautiful? Our understanding of the fundamental laws of nature is a remarkably recent development, not just on the evolutionary timescale, but even in the short span of human history. What's more, to access these laws, we need to build fantastically sophisticated instruments, microscopes to probe the infinitesimally small, telescopes to pierce the cosmic darkness, and powerful computers to crunch through impossibly long chains of mathematical reasoning. Mathematics itself isn't hardwired into our brains. It's a language we have to learn. And yet, despite all that, our innate sense of the aesthetic, our capacity for beauty, responds profoundly to the fundamental workings of nature. It presents itself as a kind of mystical unity, an inexplicable harmony between the human mind and the material world. Could it be, as some have wondered, a hint of something divine? The great German philosopher and mathematician Gottfried Wilhelm Leibniz once suggested that the imperfection we perceive in the world is based only on our knowing too little of the universal harmony of the universe and the hidden reasons for God's activity. He was suggesting that what we see as flaws are just parts of a grander, more intricate design that our limited minds cannot yet comprehend. Consider a discovery made in the deep, silent waters off the coast of Japan starting back in 1995. Divers exploring the seabed began to find these exquisite, perfectly circular patterns crafted from sand, each about 2 meters in diameter. For nearly 2 decades, the artist behind these baffling underwater mandalas remained a complete mystery. And the eventual revelation was nothing short of astonishing. These intricate works of art were the painstaking creations of a small, rather unassuming fish, the male white-spotted pufferfish. After building his elaborate nest, the male then decorates it with shells and corals, arranging them with an almost uncanny sense of symmetry. The entire process takes about 8 days of dedicated, precise work. And you might ask, why? What is the purpose of such an elaborate and presumably exhausting display? Well, the answer is elegantly simple and profoundly important in the theatre of evolution. It's all to attract a mate. A female pufferfish will approach the nest and meticulously assess its quality, its artistry. And if, and only if, the nest meets her discerning standards, she will consent to mate. The tiny brain of this 10-centimeter fish possesses an inherent sensitivity to what we would call beauty. And the male's ability to create these mathematically elegant structures is the single most important factor in his reproductive success. Here, in the depths of the ocean, beauty is not some subjective whim. It's a genuinely enigmatic and powerful force of nature, directly shaping the future of a species. It points to a shared appreciation for aesthetic principles that goes far beyond human consciousness. Charles Darwin, the great architect of evolutionary theory, famously admitted to feeling a profound intellectual discomfort, almost a physical sickness, when he contemplated the magnificent plumage of the peacock. This extravagant, iridescent train seemed to be a direct contradiction to his theory of natural selection. It wasn't an aid to survival. If anything, it was a cumbersome liability, a come-and-eat-me sign for predators. This persistent puzzle, this anomaly, eventually forced Darwin to develop his groundbreaking idea of sexual selection. He realized that while natural selection is a struggle for existence, sexual selection is a struggle for a mate. The absurdly beautiful male peacock wasn't shaped by the need to hide from predators or find food. He was sculpted over countless generations by the aesthetic preferences of the rather plain-looking female. The cumulative choices of peahens, consistently selecting the males whose displays they found most pleasing, gradually amplified and refined the very traits that we now find so captivating. Now, Darwin, being a man of his time, found this idea difficult to fully accept, even though it was his own. His societal conditioning made it hard for him to imagine that females could be the driving force, the arbiters of such profound evolutionary change. There's a delicious irony in that, isn't there? The flamboyant male peacock undoubtedly has a much higher opinion of himself than the humble female, yet it is she who holds the ultimate power, she who shapes his very being. In the dance of evolution, natural and sexual selection are often in a delicate balance. The more conspicuous a male becomes to attract females, the more vulnerable he becomes to predators. The better he hides from his enemies, the less likely he is to catch the eye of a potential mate. Usually, a population finds a stable equilibrium between these competing pressures. But what happens if a species finds itself in a world with an almost unlimited abundance of resources and a near-total absence of natural enemies? Well, the answer is something like the extraordinary spectacle that unfolded on the island of New Guinea. This is the home of around 40 species of what can only be described as exquisitely absurd birds. You only need to experience a depiction of them to understand why they're called birds of paradise. New Guinea is a geological newcomer, having emerged from the sea only about 10 million years ago. As a result, it has very few native land mammals, and almost none that pose any threat to its bird population. And in its lush tropical rainforests, sweet fruit is available in lavish abundance all year round. This combination of factors, reduced pressure from natural selection and a glut of resources, has cranked the pressure of sexual selection up to the absolute maximum. The male birds of paradise have evolved to do little else but dance, sing, and present themselves in the most spectacular ways imaginable. Their entire existence is an elaborate performance for the purpose of attracting a mate. An existence which, I must confess, is precisely what I would be doing if I lived on such an island instead of in Rostov-on-Don. Though, perhaps on a more practical note, I might say something like, "Soon I will be filming videos for you against a backdrop of swaying palms, if my YouTube income were consistently high and stable." But alas, the landscape of online content has become so saturated that one creator can always be replaced by another. This, thankfully, is in stark contrast to the burgeoning demand for data scientists, a profession that currently holds the undisputed top position in terms of market demand. And this is hardly surprising. The recent explosion of public awareness around powerful artificial intelligences like GPT and Midjourney, well, they are all, without exception, the creations of data scientists. And from this profound societal need spring the often astronomical salaries, ranging from 200,000 to 250,000 units of local currency, and that's just an average. Crucially, there is no discernible upper limit. And given that there's a global talent shortage for this profession and that the work is often remote, you would have the flexibility to work from almost anywhere on the planet, even from an idyllic tropical island should you choose. In our current technological landscape, every skill is evaluated by two primary metrics: speed and quality. It is for these reasons that I enthusiastically recommend a specialized online intensive course, Data Science from Zero in 5 months. In just 5 months, this program promises to equip you with all the essential skills to either secure an entry-level position as a junior data scientist or to achieve a significant promotion upon completion. And this is not just a conventional online course of pre-recorded lectures. Far from it. This is an immersive experience, plunging you into real-world projects commissioned by actual clients. Over the 5 months, you will assemble a portfolio of 6 substantial projects, each designed to showcase your expertise. And throughout this accelerated learning journey, you will not be alone. Any questions or challenges you encounter can be addressed with the personalized support of a dedicated mentor, a seasoned professional with years of experience in the IT industry. The program is structured to allow you to balance your studies with your existing life. However, I must be clear, my friends, this is an intensive program. It's not something where you simply pay a fee and wait for knowledge to be miraculously downloaded into your brain. That, unfortunately, is not how genuine learning works. You will need to dedicate several hours to your studies each day. But this commitment is what allows you to aspire to a new career in just 5 months. The investment, I assure you, is truly worthwhile. I've mentioned before that my own brother works in the IT sector, and the reality of his professional life is just a different universe compared to any other form of employment I've ever witnessed. The opportunities, the dynamism, it's unparalleled. So if you feel that this path might be for you, I urge you to take the next step, navigate to the link in the description, and submit your application. And as a special consideration for our audience, using the promotional code Ali will grant you a substantial discount of 45%. Physics, as a discipline, has been almost unreasonably successful. It permeates every aspect of our daily lives. It's actually quite difficult to glance around your room and find anything that isn't, in some way, a product of its achievements. The light from your screen, the engineering of your car, the global communication networks that connect us, all of it is built on the foundations of physics. And that's because, at its core, physics provides an astonishingly accurate description of our reality. Or, so it seems, our current model of the universe is powerful enough to let us build rockets that can leave our planet and to unleash the power of the atom. And yet, at the same time, it is shockingly incomplete. Its elegant framework only accounts for and describes about 5% of the total matter and energy in the cosmos. The nature of the other 95%, the vast dark ocean of reality, remains a complete and utter mystery. What if I told you that all of this is only 5% of reality? The most profound of these discoveries is that the overwhelming source of gravity in the universe is nothing like anything we have ever encountered on Earth. This enigmatic form of energy, which we've dubbed dark energy, makes up a staggering 68.3% of the universe's total budget. All we know about it is that it is causing the expansion of the universe to accelerate. The reason we can't detect it here, in our solar system, is that it's incredibly diffuse, spread thinly and uniformly across vast cosmic distances. It's only when you consider its cumulative effect over the larger scales that its influence becomes apparent. And then there's another 26.8% of the universe, which is made up of another strange and unfamiliar substance we call dark matter. All we know about dark matter is that it rarely, if ever, interacts with itself or with ordinary matter. Crucially, it doesn't interact with light. Logically, a more accurate name might be transparent matter, but dark matter has a certain mysterious ring to it, doesn't it? It is stuck. So that leaves the final, tiny fraction, a mere 5%. That 5% is everything we know. It's the stuff that you and I are made of. It's every star, every planet, every galaxy we can perceive. And it is this 5% that is so perfectly and successfully described by the standard model of particle physics. The Standard Model is our most successful theory. It describes the fundamental interactions of all the elementary particles, the indivisible building blocks of existence. It is the bedrock. But again, it only applies to 5% of the universe. To exist knowing that we only understand 5% of reality can be a terrifying and deeply unsettling thought. And this existential discomfort has driven humanity to undertake one of the most audacious projects in its history. A collaboration of over 10,000 scientists and engineers from more than 100 countries, with an investment of over $10 billion, all came together to build a single machine, the Large Hadron Collider. This immense facility, which cost about 30 times the annual budget of the Vatican, generates no financial profit, and while almost everyone has heard of it, a great many people have no idea what it's actually for. Yet, as the great English theoretical physicist Paul Dirac once said, the investigator, in his efforts to express the fundamental laws of nature in mathematical form, must primarily strive for mathematical beauty. This statement captures the profound belief that aesthetic elegance isn't just a byproduct of truth, but a signpost pointing the way towards it. But where, one might profoundly inquire, do the females of the white-spotted pufferfish, those industrious architects of the ocean floor, acquire such astonishingly complex and multifaceted aesthetic preferences? This remains a magnificent and captivating enigma. Yet, to my discerning ear, they possess an even more enigmatic, more bewilderingly complex close relative, the male bowerbird. In stark contrast to the often flamboyant plumage and elaborate displays of many of his avian cousins, the male bowerbird presents a remarkably unassuming, even drab appearance. However, what he creates, what he meticulously constructs, is nothing short of inconceivable, astonishing, and profoundly peculiar. The males of this particular species embark on the extraordinary endeavour of building elaborate bowers, not nests for habitation, but intricate structures with carefully engineered entrances, graceful arches, distinct antechambers, and even meticulously cleared pathways leading to the main ceremonial entrance. In various strategic locations within the bower, the male fastidiously attaches clusters of vibrant flowers, artfully arranges berries, often carefully selected by colour, and constructs pristine, snow-white hillocks composed of meticulously gathered bone fragments and pieces of eggshell. And astonishingly, these are merely a fraction of his ingenious design choices. It may strain credulity to fully grasp the extent of their artistic dedication, but on occasion, male bowerbirds have been observed to actually paint their bowers. They achieve this by utilising the rich pigmented juice extracted from crushed berries, applying it with remarkable precision, often employing a leaf or a small piece of bark as a makeshift brush. Should even a single berry be dislodged from his carefully arranged masterpiece, the bird will diligently hop back and forth, tirelessly retrieving and restoring it to its precise, original position, displaying a fastidious attention to detail that mirrors the meticulousness of a human artist. Furthermore, different species of bowerbirds construct distinctly different styles of bowers, each with its own unique architectural flair. Most fascinating of all, individual birds within a single species can exhibit their own idiosyncratic styles, a unique artistic signature that sets their creations apart. And here lies the most astonishing revelation. These exquisite, painstakingly constructed gazebos serve absolutely no utilitarian function whatsoever. They are not employed as nests for laying eggs, nor do they provide shelter from inclement weather. They offer no refuge for incubating clutches or raising fledglings. Their sole, uncompromising purpose is that of an elaborate installation, a pure work of art designed for one singular objective: to impress a female. Nothing more, nothing less. But why, one might ask, is the sheer aesthetic beauty of a potential partner's creation so profoundly important to females, so critically significant that it serves as the decisive criterion in their selection process? What is even more remarkable, more profoundly intriguing, is that we, as humans, also find these creations to be inherently beautiful. Yet, we sincerely believe that all of our own works of art, our own aesthetic creations, are exclusively the products of our complex human culture. However, the reality suggests a deeper, more fundamental truth. many of humanity's aesthetic principles, our innate sense of what is beautiful, are, in fact, shared with other living organisms. Consequently, these shared aesthetic sensibilities cannot be solely attributed to cultural development. It may, of course, be a mere coincidence that we find flowers beautiful, even though their vibrant hues and intricate forms evolved primarily to attract pollinating insects, not to captivate the human eye. And unequivocally, the point is not that our brains somehow evolved from the brains of bees. Rather, it is the profound realization that both species, entirely independently of each other, have converged upon the very same universal principles of aesthetics. This shared, underlying appreciation for certain visual and structural qualities is precisely why male peacocks, with their dazzling plumage, elicit such immense pleasure in our human vision, to the extent that we are willing to adorn our own heads with their majestic feathers. Yet, the truth remains that the exquisite beauty of the peacock was, in its evolutionary design, intended solely for the discerning eyes of the females of its own species, and most certainly not for Homo sapiens. Hermann Weyl, the eminent German theoretical physicist and mathematician, once articulated a guiding principle for his own scientific endeavours. In my work, I've always tried to unite truth with beauty, but when I had to choose one or the other, I usually chose beauty. This statement, profound in its simplicity, speaks to the deeply ingrained aesthetic drives that can, at times, influence scientific thought. Now let us turn our attention to the Standard Model of particle physics, a theory that, despite its monumental, almost unparalleled success in describing the fundamental constituents and forces of the universe, is paradoxically often described by physicists as ugly. So why do the physicists who work with it despise it? Physicists, in their candid assessments, frequently express a profound dislike for its perceived lack of elegance. Paul Davies, for instance, once characterized it as ugly and contrived. Stephen Hawking, with his characteristic bluntness, labelled it ugly and accidental. And a leading figure in theoretical physics, Matthew Strassler, denounces it as ugly and ludicrous. Brian Greene laments its excessive flexibility, finding its adaptability to various phenomena a sign of its underlying inelegance. Paul Davies, in another instance, asserts that it carries the stench of unsolved problems, specifically citing the ugly feature of its uncertain and somewhat forced method of unifying the electroweak and strong interactions. Hossenfelder, in her book, recounts that she is still searching for a single physicist who genuinely likes the Standard Model. As I immersed myself in her critique, a persistent question gnawed at my mind, a question that likely resonates with many of you right now. Where, precisely, should I direct my attention to grasp this perceived lack of beauty? What specific aspects should I consider unattractive? So let us delve into the most egregious transgression of this formidable theoretical construct, a construct that, I reiterate, describes the fundamental interactions of all known elementary particles. Its most profound perceived flaw, its most unsettling characteristic, is that it is, to use the physicist's term, unnatural. It is in essence an ad hoc assembly, lacking the inherent elegance and inevitability that many believe should characterize a truly fundamental theory. I assure you, this is not hyperbole. There is even a Wikipedia article dedicated to the concept of naturalness in physics. But what precisely does this term signify? Does it imply that the Standard Model is somehow not a part of nature? That it stands apart from the very reality it seeks to describe? No. The essence of the criticism, the true meaning of unnatural, revolves around the idea that the theory's parameters and structure are too unexpectedly specific, too finely tuned, without any readily apparent compelling physical reasons for such precise values. Let us delve into a more concrete illustration to clarify this abstract concept. Imagine a hypothetical physical model that necessitates the input of 4 distinct parameters to generate a highly accurate and functionally robust model. This model, let us say, is designed to perform precise calculations and make accurate predictions regarding certain fundamental aspects of our reality. Through a series of meticulous experiments, we diligently measure the values of these 4 parameters. The results, as they emerge from the data, are as follows. 1.2, 1.31, 0.9, and then, abruptly, a staggering 4 times 10 to the power of 29. A natural, almost instinctive question would arise within you. What on earth is happening here? Why are 3 of these values so remarkably close to unity, while the 4th deviates with such an extreme, almost monstrous disparity? There is an immediate visceral sense that something is amiss, that this configuration is simply incorrect, unnatural, and frankly, unsightly. This precise discomfiture, this sense of intellectual unease, accurately encapsulates the prevailing sentiment among many physicists regarding the parameters of the Standard Model. As one theoretical physicist eloquently articulates, describing the Standard Model, it is a profoundly, extraordinarily, incredibly unnatural theory. Indeed, he goes on to label it one of the most unnatural things in physics. Drawing from the insights shared by Strassler, the current situation concerning the existence and properties of our universe can be vividly illustrated by an analogy. Consider the historical perspective on our solar system. In earlier eras, humanity largely believed that our solar system was unique, the singular planetary arrangement in the cosmos. Consequently, astronomers of that time were fervently seeking a grand theory that would naturally, elegantly, and inevitably explain the precise arrangement of the planets. Johannes Kepler, for instance, a brilliant astronomer and mathematician, was deeply convinced that anything created by a divine entity must inherently possess a profound geometric order. Driven by this conviction, he boldly hypothesized that the spheres of the planets were intricately linked by being circumscribed and inscribed within the 5 Platonic solids. These Platonic solids are in themselves truly extraordinary geometric entities. They are convex polyhedra, 3-dimensional shapes possessing the maximum possible degree of ideal symmetry. In our 3-dimensional space, only 5 such perfect forms can exist: the tetrahedron, cube, octahedron, dodecahedron, and icosahedron. They derive their enduring name from the ancient Greek philosopher Plato, who, in his profound dialogue Timaeus, posited that all matter in the physical world is composed of atoms that mirror the shapes of the first 4 of these fundamental polyhedra. The 5th, the dodecahedron, he suggested, was not merely an atomic form but rather embodied the shape of the entire universe itself. It is perhaps for this reason that the surrealist master Salvador Dalí, in his iconic painting The Last Supper, chose to depict the sacred mystery unfolding within the confines of a colossal dodecahedron, underscoring its cosmic significance. However, the knowledge of these regular polyhedra predates Plato by at least 1,000 years. For example, within the hallowed halls of the Ashmolean Museum at Oxford University, one can gaze upon an exhibit featuring 5 intricately carved stone objects, crafted approximately 4,000 years ago in ancient Scotland. These artifacts, according to one compelling theory, represent early realizations of the Platonic solids, their original purpose lost to the mists of time. So, Kepler, drawing upon this ancient wisdom and his deep philosophical convictions, put forth his theory that the precise arrangement of the planets within our solar system could be beautifully explained by the divine geometry of the Platonic solids. Yet, with the immense expansion of our astrophysical knowledge, we now understand that such a singular, naturally explanatory theory is no longer necessary. Given the almost unfathomable abundance of planetary systems scattered throughout the universe, we now grasp that there is nothing inherently natural or unnatural about the specific distances of planets from their respective stars. Such configurations are, in the grand cosmic scheme, simply a matter of statistical probability and happenstance. As Sergei Troitsky, a leading researcher at the Institute for Nuclear Research of the Russian Academy of Sciences, articulated in his incisive remarks, the Standard Model, from an insider's perspective, is quite unbeautifully arranged. It encompasses a total of 19 numerical parameters, each of which must be determined experimentally. From a perspective of conventional intellectual expectation, these parameters assume remarkably exotic values. For instance, the vacuum expectation value of the Higgs field, a fundamental constant responsible for conferring mass upon elementary particles, is found to be approximately 240 giga-electron volts. The profound mystery lies in why this parameter is an astonishing 10 to the power of 17 times smaller than the parameter that defines the strength of gravitational interaction, a discrepancy known as the hierarchy problem. The Standard Model offers no inherent explanation for this colossal disparity, this vast chasm between two fundamental constants. Furthermore, it also fails to explain the enormous mass difference between the lightest quarks, which constitute the protons and neutrons of ordinary matter, and the mass of the top quark, which exceeds 170 gigaelectron-volts. While the top quark is, in all other respects, indistinguishable from the other, much lighter quarks, it is nearly 10,000 times heavier. The origin of such seemingly identical particles possessing such vastly different masses remains for now an unresolved puzzle. One might, as a means of explanation, attribute these seemingly arbitrary values to the actions of a creator, positing a fine-tuned universe, where a divine entity meticulously adjusted the parameters of the cosmos to allow for its very existence in the form we perceive. However, such an explanation, while offering a sense of closure, ultimately satisfies few within the scientific community, as it effectively halts further inquiry. Alternatively, one could contend that just as there are countless solar systems, there are likely innumerable universes, each with its own unique set of physical parameters. In this grand cosmic lottery, we simply happen to reside in one particular universe among an infinite spectrum of possibilities. Many physicists, indeed, adopt this very perspective. While this could certainly be the truth, it remains deeply unsatisfying to some, as it offers no clear pathway for experimental verification. Yet, a substantial number of physicists, perhaps driven by an inherent aesthetic or intellectual conviction, firmly believe that beneath this apparent chaos, this seeming arbitrariness of parameters, lies a deeper, coherent, and profoundly intelligible system. A system that we, with our current limited understanding, simply have not yet unveiled. Werner Heisenberg, one of the foundational figures of quantum mechanics and a Nobel laureate, articulated this sentiment beautifully. When nature itself suggests mathematical forms of great beauty and simplicity, one is involuntarily led to believe that they are true, that is, that they express real features of nature. This statement encapsulates the profound faith that many scientists place in the power of aesthetic intuition as a guide to fundamental truth. Consider, for a moment, an image, perhaps a pattern of seemingly random spots. Your initial impression might be one of complete disarray, a chaotic jumble of forms. But then, an extraordinary process unfolds within your brain. Something shifts, something clicks, and suddenly, order emerges from the confusion. Everything falls into its rightful place. Your brain has performed the very function for which it painstakingly evolved over millennia. It has assembled the disparate pieces of a puzzle, and in doing so, it rewards itself with a subtle, yet distinct surge of gratification. You might not have consciously registered this moment, but when you finally recognize the image as a Dalmatian dog, perhaps sniffing intently at the ground, you experienced a faint prickle of pleasure, an internal exclamation of "Ha!" as if you had successfully solved a perplexing problem. This powerful principle, known as the law of grouping, was first elucidated by Gestalt psychologists in the early part of the last century. This fundamental cognitive mechanism is not confined to the abstract realm of psychology. It is skillfully employed by artists, designers, and even fashion professionals across various disciplines. In some of the most celebrated paintings of the Renaissance, for instance, a specific shade of azure blue might be intentionally repeated across the canvas, appearing as part of various seemingly unrelated objects. Similarly, the same recurring colour might be utilised in the halos of saints, the folds of their garments, and the flowing strands of their hair. The astute artist, rather than employing an endlessly diverse palette of colours, deliberately limits their selection. They understand that the human brain craves and derives pleasure from this very act of perceptual grouping, just as it found satisfaction in organising the scattered spots of the Dalmatian into a coherent form. The same underlying principle extends elegantly into the realm of fashion. When an individual, perhaps a young woman, ventures into a boutique with the intention of purchasing a vibrant red skirt, an experienced and perceptive sales associate will instinctively suggest a complimentary red scarf. Similarly, almost every man, when selecting a necktie, intuitively understands that a particularly stylish choice involves matching its colour to the subtle hues of his eyes. The pervasive influence of the law of grouping therefore clearly indicates something profoundly fundamental about the organisation and functioning of the human brain. But why do we possess this peculiar and computationally incredibly complex ability? The answer lies deep within our evolutionary history. Grouping mechanisms evolved as a crucial survival strategy, enabling our ancestors to overcome camouflage and detect vital objects amidst a chaotic environment. If I were to ask you, what is the purpose of your vision, you might offer a poetic response, something akin to bear witness to the grand tapestry of existence. While undeniably beautiful, the raw truth is that vision, from an evolutionary perspective, primarily developed for much more pragmatic, survival-oriented functions. To identify, to deftly avoid, to relentlessly pursue, to effectively consume, and to successfully mate with other objects and organisms in the environment. Imagine for a moment your ancient ancestors confronted with a complex visual scene, a dense thicket of foliage. In a mere fraction of a second, their brains would engage in an internal monologue, a lightning-fast computation. What is the probability that all these fragments of the same colour are simply a pure coincidence? Let us assume that probability is 0, just in case. Yes, let's proceed on the assumption that they belong to one and the same entity. Therefore, I shall mentally glue them together to form a coherent shape. Oh dear, it seems I need to flee. This seemingly mysterious ability to mentally group disparate visual elements, to connect the dots, so to speak, quite literally represented the difference between life and death in the wild. When we meticulously select clothing and accessories with taste, many of us remain entirely unaware that we are in fact enacting a profound principle deeply embedded in the organizational structure of our brains, specifically the ancient life-saving capacity to discern and identify predators. Edward Arthur Milne, the distinguished astrophysicist, eloquently stated, "Beauty is a road to knowledge, or more precisely, the only knowledge worth possessing." This profound sentiment encapsulates the conviction that aesthetic appeal is not merely superficial, but a powerful guide to deeper truths. In their pursuit of a Dalmatian, a coherent pattern from the chaos, physicists attempted to assemble the puzzle. They extended the standard model, christening their proposed expansion with an appropriately beautiful name, the hypothesis of supersymmetry. Supersymmetry, in its theoretical formulation, appears far more natural and promises to resolve many of the perplexing problems currently afflicting modern physics. However, despite the frequent utility of its intricate mathematical apparatus across diverse branches of physics, supersymmetry, as of now, exists solely on paper, a collection of elegant mathematical formulas. The colossal Large Hadron Collider, a $10 billion endeavour constructed with the explicit aim of experimentally confirming its existence, has, contrary to the confident expectations of many physicists, thus far yielded no tangible evidence of supersymmetric particles. This absence of empirical validation presents a significant challenge to the theory's status as a description of physical reality. What if we've reached the end? What if we simply can't know? In 1930, Wolfgang Pauli, a brilliant and somewhat reluctant physicist, postulated the existence of a new elusive particle, the neutrino. His bold hypothesis was conceived as a desperate last-ditch effort to explain the mysterious and perplexing loss of energy observed during radioactive decay processes. He famously described his own proposition as a desperate remedy and confessed to his colleague, the astronomer Walter Baade, "Today, I have done something terrible, something no theoretical physicist should ever do. I have hypothesized a particle that can never be confirmed or refuted experimentally." Yet history, in its own unpredictable way, often writes surprising conclusions. The existence of the neutrino was, against Pauli's initial pessimistic assessment, experimentally confirmed a mere quarter-century later. Hossenfelder critically notes that, ever since Pauli's initial, groundbreaking, albeit reluctant, act of postulating a new particle, this practice has become the preferred pastime, the beloved intellectual pursuit of theoretical physicists. The scientific literature is now replete with a bewildering array of hypothetical particles, axions, simps, strongly interacting massive particles, WIMPs, weakly interacting massive particles, and so forth. We even possess entire categories of unparticles, conceptual entities that exist purely within the mathematical framework of theory. Yet, not a single one of these has ever been conclusively detected. Despite this complete absence of empirical evidence, their intricate properties are meticulously described in thousands upon thousands of published scientific articles, forming a vast self-referential web of theoretical possibility. Hossenfelder asserts, with a bluntness that underscores her frustration, that physicists have conjured unimaginable theories. She observes that, throughout her 2 decades in theoretical physics, the vast majority of her acquaintances and colleagues have forged successful careers by diligently researching phenomena that no one has ever actually observed. The prevailing strategy, she explains, is to postulate that the creation of one's hypothetical particle would require an extraordinarily high energy threshold, or that it interacts so infrequently and weakly with ordinary matter that the sensitivity of existing detectors is simply insufficient to register its presence. Often, both conditions are invoked simultaneously. For example, the most widely accepted explanation for the pervasive enigma of dark matter is that it consists of some as yet undiscovered type of particle. However, a crucial question remains. Who definitively stated that dark matter must, by its very nature, be composed of particles? Observations of certain galaxies, for instance, reveal specific patterns and irregularities that a dark matter model composed solely of particles is simply incapable of explaining. If we strictly adhere to the particle-based dark matter model, we find ourselves unable to account for various cosmic anomalies. For instance, we cannot adequately explain why our own Milky Way galaxy possesses fewer satellite galaxies than predicted by simulations, or why the existing ones are found to lie almost entirely within a single highly flattened plane. It is possible, of course, that these perceived flaws in our understanding are merely artifacts, products of astrophysical processes that have not yet been properly incorporated or fully accounted for within our current finely tuned cosmological model. Or perhaps they are telling us something far more profound, that we are fundamentally misunderstanding something about the universe itself, that our theoretical framework is missing a crucial piece of the cosmic puzzle. The terrifying question, one that most scientists likely strive to avoid contemplating too deeply, is this. What if we have, in fact, reached the absolute limits of experimental verifiability? It might very well be that in order to definitively confirm certain hypotheses, we would require a particle collider of unimaginable scale, perhaps one the size of Jupiter, orbiting a neutron star. According to the author of the book, such a colossal apparatus would be necessary to even hope to detect the graviton, the hypothetical quantum of the gravitational field. What then are we to do if we are no longer capable of empirically testing our grand hypotheses? Deprived of this essential capacity to turn the wheel of scientific progress, some theoretical physicists have, quite remarkably, invented their own idiosyncratic method for evaluating theories, concluding by decree. Sean Carroll, a renowned cosmologist, is famously willing to bet his dog on the existence of the multiverse. Andrei Linde, another prominent cosmologist, is prepared to wager his entire life on it. And Steven Weinberg, a towering figure in physics, professes such a high degree of certainty in the multiverse that he is willing to stake the lives of both Andrei Linde and Carroll's dog on its validity. And here lies a truly ironic twist. This is the same Steven Weinberg who, at an earlier point in his illustrious career, famously asserted that the interpretation of general relativity was utterly devoid of significance. He dismissed the concept of space-time curvature as empty poetry, arguing that the only thing that truly mattered was whether a theory yielded successful predictions. David Deutsch, in his profound and influential book The Fabric of Reality, was a vocal critic of such instrumentalist views and specifically called out Weinberg, casting doubt on the underlying motivations behind his philosophical stance. It appears Deutsch was not mistaken. Weinberg, a co-creator of the Standard Model, clearly had an innate need for a coherent and elegant picture of the world, even if that picture could not be experimentally verified, and even, remarkably, if it offered no new predictive power. This suggests a powerful, perhaps unconscious, drive for aesthetic and intellectual completeness, even in the absence of empirical support. George Ellis, an esteemed honorary professor at the University of Cape Town and a leading figure in the field of cosmology, observes that a disturbing trend has emerged in contemporary physics. He notes that there are now physicists who openly or implicitly declare that their ideas do not require the crucible of experimental verification, simply because their ideas are, in their estimation, inherently so good. Ellis staunchly believes that any weakening of the criterion of falsifiability, the requirement for theories to be testable, would constitute a catastrophic regression for science, effectively setting it back a millennium. But what if, just what if, this perspective is flawed? What if we are mistaken? Why are we so reluctant to assert that there exists something intrinsic within the very architecture of our brains, a capacity that can guide us towards a correct understanding of the world, bypassing the necessity of every single experiment? What gives us such unwavering certainty that all knowledge is acquired solely through empirical means? Are you absolutely convinced that you possess no innate, hardwired knowledge about the world? Why are we so adamantly convinced that Einstein was incorrect when he mused about the capacity of pure thought, by itself, to unveil the fundamental laws of nature? Allow me to present a more complete, a more nuanced excerpt from his profound statement that opened this discussion. Einstein, with his characteristic blend of philosophical insight and scientific rigor, articulated, "Preceding experience convinces us that nature is the realization of the simplest mathematically conceivable elements. I am convinced that through purely mathematical constructions, we can find those concepts and the lawful connections between them that will give us the key to understanding the phenomena of nature. Experience can suggest the appropriate mathematical concepts to us, but they can in no way be deduced from it. Of course, experience remains the sole criterion of the suitability of mathematical constructions in physics, but the true creative principle lies in mathematics," he continued. "Therefore I consider the belief of the ancients, that pure thought is capable of grasping reality, justified in a certain sense." But who were these ancients, of whom Einstein spoke with such reverence? His reference unmistakably points to figures like Plato, who, in his celebrated dialogue Meno, brilliantly illustrated the presence of innate knowledge within humanity, knowledge that exists within us prior to any empirical experience. Plato's argument is delivered with remarkable persuasive power, particularly through the compelling example of a conversation between Socrates and a young, uneducated slave boy. This boy, utterly ignorant of geometry, yet guided by Socrates' skillfully posed questions, and without any direct hints or explicit instruction, independently arrives at a clear and accurate formulation of the Pythagorean theorem. He achieves this profound insight purely through the process of thoughtful reflection and logical deduction. This raises a truly fundamental question. How can an individual, utterly devoid of any formal geometric training, possess such an accurate and correct intuition regarding geometric figures? This intellectual feat, achieved purely through internal reasoning, deeply challenges the notion that all knowledge is derived solely from experience. After encountering this compelling dialogue, a question spontaneously arose in my own mind, a question that perhaps has never truly occurred to you. Have you ever paused to truly ponder what geometric figures actually are? Seriously, what are they? Why does no one, across diverse cultures and educational backgrounds, experience any difficulty whatsoever in grasping the very concept of a triangle, a circle, or a square? From an evolutionary perspective, geometric figures are, to put it mildly, not something that ubiquitously appears in their perfect, idealized forms throughout nature. If, for example, we were to discover a perfectly formed pyramid on the surface of Mars, you can be certain that every scientist and observer would immediately declare it to be an artificial structure, an undeniable product of intelligent design rather than a natural geological formation. The mysterious hexagonal storm at Saturn's North Pole, for instance, a naturally occurring six-sided cloud pattern, continues to perplex scientists. We are still striving to fully comprehend its origins and enduring stability. This highlights our inherent bias. Geometric perfection implies design. It is relatively straightforward to explain why, from an evolutionary standpoint, a landscape panorama, perhaps a verdant valley with a flowing river, bathed in warm sunlight, surrounded by lush trees, is universally perceived as beautiful and elicits feelings of pleasure and comfort. Such an environment contains all the essential elements that aided the survival of our ancestors: readily available water, life-sustaining sunlight, and shelter-providing trees. These are immediate, tangible benefits. But how then do we explain why we find abstract patterns, intricate fractals, or complex mathematical equations beautiful? What evolutionary advantage is derived from appreciating these forms? Leon Lederman, a distinguished physicist and Nobel laureate, famously asserted, "We believe that nature is best described by equations that are as simple, beautiful, compact, and universal as possible." This profound statement encapsulates the aesthetic ideal that guides many physicists in their quest for fundamental theories. Consider for a moment the magnificent architectural wonders of antiquity, those grand structures that continue to inspire awe and admiration. Yet, we often forget a crucial fact. We only perceive those structures that, against all odds, have managed to endure the ravages of time. The vast majority of ancient constructions, particularly the more innovative or experimental ones, crumbled and fell, often very shortly after their completion. This widespread failure stemmed from a fundamental limitation. Ancient architects and builders relied upon a rather specific blend of intuition, accumulated empirical skills, and implicit, often unarticulated theoretical dependencies. These constituted their engineering knowledge, but it was a knowledge that was not yet sufficiently complete, not deep enough, and certainly not distilled and refined to its purest essence. The ancient builder, for all his practical skill, would have been largely incapable of articulating the vast majority of this knowledge in the precise language of mathematics and physics. He could not have written down the fundamental principles in the form of elegant equations. Consequently, he would have been utterly unable to definitively explain why the grand edifice he so painstakingly constructed ultimately collapsed. Conversely, if 1,000 individuals were to read a complex literary work, they would in effect each read 1,000 different books, each interpreting the narrative through the unique lens of their own experiences and understanding. But if 1,000 individuals were to read a single mathematical equation, they would, without exception, read the exact same equation. Such is the clarity and precision of mathematical language, stripped bare of all ambiguity and subjective interpretation. It is for this very reason that today it is an exceedingly rare occurrence for a structure, even one of unprecedented design or complexity, to collapse due to a fundamental flaw in its construction. Our refined, deeply theoretical knowledge, our ability to precisely model and predict the behavior of materials and forces, allows us to erect structures that ancient architects could scarcely have dreamt of. Colossal skyscrapers that pierce the clouds, or intricate space stations that orbit our planet. The modern engineer possesses such a profound and comprehensive understanding of the fundamental principles governing the universe, particularly in the domain of structural mechanics and materials science, that they can confidently apply these principles to virtually any conceivable construction project. Whether the edifice is to be fashioned from novel alloys or traditional stone, whether it is to be situated on the lunar surface, beneath the crushing pressures of the deep sea, or in any other extreme environment, our refined theoretical knowledge allows us to design with an unprecedented degree of reliability. If, for the past 5 minutes, you have felt as though I have been meandering through a collection of seemingly disparate and unconnected ideas, then firstly I extend my profound gratitude for your patience. And secondly, allow me to clarify my underlying intention. I mean to convey that our innate human capacity to discern patterns, to identify underlying regularities, to relentlessly delve into the very essence of phenomena, and crucially to derive a deep sense of pleasure from this very act of comprehension. This ability is profoundly integrated into the very fabric of our being. All these points, lines, triangles, and other fundamental geometric forms are, in essence, one of the primary ways in which we, in our mental representations, deconstruct matter into the simplest, most fundamental building blocks of reality. They represent the most basic forms that matter can assume. Indeed, try to conceive of something simpler than a triangle. If we are speaking of a closed rectilinear figure, it is, by definition, impossible. By meticulously ascertaining the principles by which these most elementary blocks exist and interact, we can then begin to comprehend how the complex macrosystems composed of them operate. In this manner, we strive to extract the very essence of reality, to grasp its fundamental truths. And as you have undoubtedly gathered, this inherent drive to extract the core essence is not unique to humanity. It is a shared, fundamental characteristic found throughout the animal kingdom. Consider a carefully designed experiment involving a rat. The rat is repeatedly presented with the task of distinguishing a rectangle from a square. Each time the animal correctly approaches the rectangle, it receives a small rewarding piece of cheese. Conversely, if it gravitates towards the square, it receives no such reward. After several dozen trials, the rat, through a process of trial and error and association, develops a clear understanding. The rectangle signifies food. It then ceases to pay attention to the square and consistently navigates only towards the rectangle. In essence, the rat has developed a preference for the rectangle. But here's the crucial next step. If you then present this same rat with a new rectangle, one that is significantly longer and thinner than the original rectangle it was trained on, the rat will now exhibit a stronger preference for this new rectangle rather than the original one. Far from being foolish, the rat in fact demonstrates a remarkable degree of intelligence and an acute capacity for generalization. It has grasped the very essence of the pattern, the underlying regularity of rectangularity. It chooses the second rectangle because, in its perception, it embodies more of what makes a rectangle distinct from a square, a greater degree of rectangularness, if you will. The more you amplify the contrast between the rectangle and the square, the more attractive the rectangle becomes to the discerning rat. This ability to extract the core essence, to identify and generalize fundamental patterns, is profoundly advantageous from an evolutionary perspective. It is therefore entirely unsurprising that we, and many other species, derive pleasure from this very act of discerning and comprehending underlying structures. Perhaps geometric figures, in their purest, most fundamental forms, appeal to us precisely because they represent the most basic geometry that can possibly exist, at least according to our human cognitive framework. It is likely for this same profound reason that we find caricatures so compelling and amusing. Have you ever truly pondered the astonishingly complex task involved in recognizing faces, and doing so with almost instantaneous precision? Most likely not, because for you, this intricate cognitive process occurs with such effortless ease. The human brain, more than almost any other biological function, is evolutionarily honed and meticulously specialized for this very task. Many people tend to conceptualize the environment in which a biological organism exists as something composed primarily of abiotic factors such as water, soil, and air. However, a vast and critically important component of the environment for almost any biological organism is, in fact, other biological organisms. For humans, an enormous and profoundly influential part of our environment consists of other human beings. It is entirely plausible, in fact, highly probable, that our ancient ancestors far more frequently met their demise at the hands of members of their own species than from any other predators. Consequently, we developed an almost unbelievable capacity for facial recognition, if for no other reason than to precisely differentiate between our own kin and strangers, friend and foe. Yet, despite the immense importance of this ability, human faces are, when objectively considered, remarkably similar. If one were to truly contemplate the matter, the subtle distinctions that differentiate one human face from another are often remarkably minute. Nevertheless, We very rarely, if ever, looking at faces, mistake one person for another. And consider this. Over the course of a lifetime, we encounter millions of faces. For an extraterrestrial visitor, unaccustomed to our species, these faces would likely appear to be only faintly distinguishable from one another. From each individual face, our astonishing brain endeavours to extract the absolute, most fundamental essence, the core pattern, in order to reliably recognise it later. Caricatures in this context appeal to us precisely because they lighten this titanic cognitive load on the brain. A caricaturist, when depicting a figure like Nietzsche, adeptly extracts all the salient patterns and distinctive features that our brain utilises to recognise the great philosopher, and then exaggerates them in their portrayal. In essence, the caricaturist might conceptually take the average of all male faces, subtract it from Nietzsche's face, and then amplify the resulting differences. In doing so, they create a portrait that, in a profound cognitive sense, is more like Nietzsche than Nietzsche himself. For precisely the same reason, we are captivated by films. They do not merely replicate reality in a documentary fashion. If they did, few would find them engaging. No one would willingly choose to observe mundane daily routines unfolding on a screen. A compelling story, meticulously crafted and presented in cinema, skillfully extracts the most crucial elements, discarding all the superfluous details. It provides a concentrated essence of reality, a distillation of experience that resonates more powerfully than unedited life. The same principle extends to books, games, visual art, and indeed, every manifestation of human creativity. A significant number of theoretical physicists harbour the profound conviction that the real world, the ultimate underlying reality, is governed by a single, mathematically coherent and intrinsically beautiful theory. This singular theory, they believe, must inherently permit the existence of a vibrant, diverse world, a multitude of complex phenomena, and a rich, unfolding history. This profound idea resonates deeply with the ancient philosophy articulated by Plato in his foundational work, The Republic. Plato famously contended that our sensory world, the world we perceive with our physical senses, is not truly real. It is merely a shadow, an imperfect reflection of a more fundamental, more real domain, the world of ideas, or forms. When, for instance, you utter the word sofa without referring to any specific tangible piece of furniture, and another person comprehends precisely what you're discussing, at that very moment, both of you are contemplating the sofa not with your physical eyes but with your minds. You're engaging with the idea of a sofa. All existing sofas, regardless of their individual appearance, their specific fabric or their particular design, are merely imperfect projections, material manifestations of that singular ideal sofa, which exists not in our tangible world, but in the one true ultimate reality of ideas. And as you have undoubtedly gathered, this profound world of ideas, this realm of pure forms, can only be apprehended and understood through the intellect, through the power of pure thought. While this concept might at first sound abstract or even counterintuitive to some, it is precisely physicists who have advanced Plato's original vision further than anyone else. When Max Tegmark, a physicist from the Massachusetts Institute of Technology, posits that the universe is not merely well described by mathematics, but is, in its very essence, mathematics itself. What is this if not a direct continuation, a profound legacy, of Plato's foundational philosophy? It suggests a universe whose deepest structure is inherently logical and mathematical, accessible to the human mind through reason. However, Sabine Hossenfelder, with her characteristic pragmatism, argues that the notions of a multitude of universes, or a single, unifying law of everything, remain for now merely beautiful dreams. They are possibilities, she contends, that may or may not ultimately prove to be true. She specifically criticizes the criterion of naturalness as an unreliable starting point for theoretical inquiry. In an interview for her book, the late Steven Weinberg, who, ironically, once claimed indifference to the interpretation of general relativity, responded to Hossenfelder's objections with a thoughtful yet speculative counter-argument. He posited, "I don't know. Perhaps a true theory allows for the emergence of many Big Bangs in the early stage of the universe." He continued, In these big bangs, occurring simultaneously, the physical constants differ significantly, and we will never be able to predict what they are in other big bangs from within our own. It is not excluded that there is an unlimited number of big bangs, and the values of the physical constants in our particular big bang are simply those that happened to randomly occur. This, he suggests, would naturally explain the unnaturalness of our universe's parameters. This perspective presents a stark dichotomy. Either the universe is fundamentally unnatural, meaning its parameters are arbitrarily fixed by chance, or the multiverse exists. There is, in this view, no third option. If we are unable to detect supersymmetric particles in the Large Hadron Collider, then, according to this line of reasoning, we must, by logical deduction, reside within a multiverse. This, Hossenfelder notes, represents the viewpoint of many physicists today. V.S. Ramachandran, an eminent professor of psychology and neurophysiology at the University of California, in his insightful book The Telltale Brain, meticulously explores the profound challenge of discovering universal laws of aesthetics. He posits that these laws do not always possess an independent, standalone function. Rather, they may, in many instances, be merely incidental byproducts, unintended consequences, of other underlying biological or cognitive laws that do serve a direct evolutionary purpose. Indeed, at times it might even appear that certain aesthetic principles contradict each other to an absurd degree. For example, one might intuitively assume that for a heterosexual male, a completely unclothed female form would be perceived as maximally attractive. However, in reality, the opposite is often true. A partially concealed body, rather than a fully exposed one, more effectively activates our visual processing centers and is often perceived as significantly more alluring. This phenomenon applies equally to both sexes. We exhibit a preference for such partial concealment because our brains are fundamentally wired to enjoy solving puzzles. Perception itself, Ramachandran argues, is far more akin to a problem-solving exercise than most people realize. The act of solving a puzzle, whether it be a purely intellectual challenge like a crossword or a logical riddle, or even a purely visual one like identifying a camouflaged object, often provides a subtle sense of pleasure, even before the solution is fully grasped. Without this intrinsic motivation, this preemptive reward, we would, as a species, likely abandon most challenging tasks far too quickly. Consider the arduous problems faced by our ancestors. How to convince a potential mate to return to your cave and gaze at your fire, or how to relentlessly pursue that elusive prey through tall grass in a dense fog. Without an innate drive to solve these problems, a partial satisfaction in the pursuit itself, our species would have succumbed to the challenges of survival. The Telltale Brain is the second book I extensively utilized in crafting this monologue. While I've only acknowledged it explicitly just now, its profound insights permeate the entire narrative, from its very beginning to its conclusion. It was specifically Ramachandran's deep dive into the neurophysiology of perception that enabled me, to the fullest extent possible, to unravel and comprehend the enigmatic and often contradictory concept of beauty. It is a concept so fraught with paradox that our brain simultaneously embraces and perhaps surprisingly loathes coincidence. Consider this image. A seemingly random arrangement of 3 circles, each with an identical Pac-Man shaped cutout. Your brain immediately engages in an internal calculation. What is the probability that these 3 circles with their identical missing wedges are positioned in precisely this manner purely by chance? The answer, your brain implicitly asserts, is not chance. This is incredibly unlikely, far too suspicious a coincidence. It demands a simpler, more overarching explanation. And that explanation emerges, a solid white triangle, visually occluding parts of the 3 black discs. This interpretation is far more plausible, far more natural, and so you perceive a triangle even though no actual lines are drawn to define it. Your brain, so exquisitely honed for puzzle solving, renders a judgment about what is more probable, what is less, even without your conscious participation. In the wild, attributing a seemingly random event to a deeper non-random cause, even if incorrect, is often a life-saving heuristic. Consider for a moment 2 contrasting scenarios. Which of these two situations would unconsciously trigger a sense of wariness or alarm within you? The answer, intuitively, is obvious. The human brain abhors coincidences that it cannot readily interpret or explain. Yet, on the other hand, imagine a picture hanging slightly askew on a wall. An immediate disproportionately negative reaction arises, far exceeding the actual magnitude of the deviation. Or a drawer that refuses to close completely due to a tiny piece of paper jammed and protruding. Or an envelope, meticulously sealed, with a single hair accidentally caught and adhering to the glue. Or a minuscule fleck of lint marring an otherwise impeccably tailored suit. Why do all these minor imperfections elicit such profound feelings of displeasure? Some of these reactions might be attributed to elementary hygiene, a composite of instinctive and learned behaviours. The desire to remove a stray piece of lint from a child's hair, for instance, might have deep roots in the instinctive grooming behaviours observed in primates. Other examples, such as a crookedly hanging picture or an uneven stack of books, seem to point to an innate hardwired necessity within our brains for order, for correctness, or for predictability, a fundamental drive to impose order upon chaos. Thus, we discern a profound convergence. The pursuit of beauty, in its deepest sense, often leads us to the very same choices and preferences that are fundamentally useful and adaptive for our survival and well-being. Jules Henri Poincaré, the brilliant French physicist and mathematician, perhaps most renowned for his groundbreaking discovery of deterministic chaos, made a profound observation that intertwines these concepts. Sabine Hossenfelder, in her provocative book Lost in Math, makes an utterly scandalous claim that Karl Popper's venerable idea, the principle that scientific theories must be falsifiable, meaning they must be capable of being disproven by experiment, has long since become an outdated and impractical criterion for modern science. Moreover, she argues that, in reality, this principle has rarely, if ever, been truly applied in the field, except as a rhetorical device. The sobering truth, she contends, is that genuinely and definitively refuting a theory proves to be an exceedingly rare accomplishment. Consequently, instead of definitively falsifying theories, what we actually do, Hossenfelder explains, is gradually render them implausible. A theory that is continuously being reconfigured, perpetually adjusted to accommodate contradictory data, progressively becomes more intricate, more convoluted, and, one might even say, less aesthetically appealing, less beautiful. Eventually its adherents, faced with an ever-growing edifice of complex additions and adjustments, simply lose interest. The time required to render an idea implausible, she notes, is directly proportional to the prevailing tolerance for repeated adjustments of the theory to fit contradictory data. Sabine Hossenfelder, I reiterate, is absolutely incandescent in her critique. In essence, this iterative process of patching and tweaking, rather than outright refutation, is precisely what she believes is currently transpiring with the hypothesis of supersymmetry. So, let us delve into the profound significance of symmetry. This damned symmetry is one of the most critical principles deeply ingrained within the very structure of our brains, and it holds immense importance throughout the natural world. Why is it so crucial? Because significant biological objects, whether they be prey animals, dangerous predators, or potential mates of one's own species, all share a common, defining characteristic. They are to a remarkable degree symmetrical. This fundamental observation elegantly explains why symmetry so powerfully captures our attention and stimulates our cognitive and emotional responses. Similarly, it illuminates why artists and architects, across cultures and epochs, have been able to employ symmetry with such consistent success, creating works that universally resonate with a sense of balance and harmony. This inherent preference for symmetry is evident from the earliest stages of human development. A newborn infant, for instance, will instinctively fixate on symmetrical ink blots rather than asymmetrical ones. This innate preference, observed even in the youngest of us, testifies to a fundamental infant law, a pre-programmed cognitive rule that seems to declare something symmetrical? That seems important. It warrants further observation. A second evolutionary reason for our deep-seated appreciation of symmetry is more subtle, more elusive. Psychologists presenting a randomized sequence of faces with varying degrees of symmetry to graduate students discovered a consistent pattern. The most symmetrical faces were invariably rated as the most attractive. This finding in itself is hardly surprising. However, what proved truly interesting was the observation that even the most minute deviations from perfect symmetry were often perceived as distinctly unappealing. Why this exquisite sensitivity, this intolerance for even the slightest imperfection in symmetry? The answer, as it turns out, we owe to the ubiquitous presence of parasites. Parasitic infections can dramatically diminish an individual's fertility and overall reproductive success. Consequently, evolution has conferred a significant advantage, a high reward, upon the capacity to accurately discern whether a potential mate is infected. If the infection occurred during gestation or early childhood, one of the most subtle, yet telling, external indicators of this compromised health is precisely and almost imperceptible asymmetry in physical features. Therefore, symmetry serves as a powerful, ancient marker of robust health, which, in turn, is a reliable indicator of reproductive fitness and overall attractiveness. Is the profound, deep-seated human necessity to avoid parasites somehow connected to the whimsical, architectural caprice of the magnificent Mughal emperor, who decreed the construction of the exquisitely symmetrical Taj Mahal as a sublime symbol of eternal love? And is this same biological imperative linked to the almost obsessive commitment of scientists to the pursuit of symmetrical equations? Why not? The human brain, in its remarkable plasticity, is entirely capable of utilizing the same neural regions, the same cognitive pathways, for both tangible, real-world experiences and abstract concepts. For example, it has been experimentally confirmed that the feeling of moral revulsion towards a contemptible act and the visceral feeling of disgust towards spoiled food both activate the exact same regions of the brain. This suggests a deep underlying connection between our physical and moral judgments. Let us consider this from an alternative perspective. My mother, with her characteristic pragmatism, often quips that symmetry is aesthetics for the dull-witted. Now, if I were to assert to you that a truly beautiful and fundamental theory, one that truly describes the cosmos, is, in fact, inherently chaotic and profoundly asymmetrical, that statement might, at first, sound unconvincing, perhaps even absurd. However, this assertion would gradually sound more and more compelling each time you heard it. Research consistently demonstrates that we tend to perceive a statement as truer, more veridical, the more frequently we are exposed to it. This cognitive phenomenon is known as the attentional bias, or the familiarity effect. What is both fascinating and, depending on one's perspective, rather disheartening, is that this effect operates even when the repeated assertion comes from the exact same individual. The truth, perhaps, is that chaos, in a subtle and nuanced way, possesses a beauty that transcends rigid symmetries. Have you not yet fully embraced this provocative assertion? Why are certain deviations, such as a picture hanging askew, considered unattractive, while other forms of asymmetry, say an exquisitely placed beauty mark on a person's face, are perceived as highly attractive? A birthmark positioned precisely in the middle of the chin or nose, for instance, is indeed often not perceived as favourably. Ramachandran, in his work, acknowledges that we do not yet possess a definitive answer to this apparent contradiction. It is possible that the explanation lies in our inherent preference for a delicate balance, a nuanced equilibrium between dull, predictable order and overwhelming, terrifying chaos. Ultimately, novelty itself is beautiful, but only if it does not demand an excessive cognitive load from the perceiver. We desire to be surprised, to encounter the unexpected, but not to an overwhelming degree. And you would be astonished by how much of your daily life, how many of your preferences and reactions are governed by this precise formula. In your school years, you invariably and acutely recognized the precise moment when a teacher articulated something that was already perfectly clear and understood. You also distinctly recognized the moment when a teacher introduced a truly novel concept, and you comprehended it with crystalline clarity, seamlessly integrating new knowledge into your existing understanding. And then there was that irritating, frustrating moment when you completely ceased to understand the subject matter, plunging into a state of total, bewildering meaninglessness. Yet once you painstakingly deciphered the concepts, once you grasped the underlying logic, you experienced a profound rush of pleasure, a deep satisfaction born from finally imposing control over intellectual chaos. This delicate balance, this perpetual negotiation between order and disorder, is precisely where modern physics currently finds itself, or is on the verge of finding itself. Such are the formidable rules of this intellectual game. If your aspiration is to discover a theory of everything, then your aesthetic sensibilities, your innate sense of beauty, are arguably the single most critical tool you must rigorously refine and work with. Garrett Lissy, the American theoretical physicist, whose work explores the connections between fundamental physics and exceptional Lie algebras, embodies this philosophy. And the situation would not be so acutely problematic if we were solely constrained by universal, objectively verifiable criteria of beauty. However, it very often transpires that what one individual perceives as profoundly interesting and beautiful, another dismisses as mundane or unappealing. Why do we, as ordinary individuals, experience a sense of intellectual irritation or blank incomprehension when confronted with Maxwell's equations, those elegant formulations of electromagnetism? Yet Frank Wilczek, a Nobel laureate in his book, describes their beauty as utterly beyond words. Ludwig Boltzmann, another towering figure in physics, contemplating Maxwell's equations, famously exclaimed, "Was it a god who traced these lines? Why do a staggering 99% of physicists regard Einstein's general theory of relativity as one of the most beautiful theories in the entire history of science, while an equally vast 99% of the planet's population, even with the greatest desire, are simply incapable of comprehending it to a sufficient degree?" This profound disparity in perception might be explained by the hypothesis of neural efficiency. Research consistently demonstrates that the brains of individuals with higher IQs exhibit less activity and consume less glucose when performing tasks of moderate complexity. Conversely, these same brains display greater activity when tackling genuinely complex problems compared to individuals with lower IQs. This strongly suggests that more intelligent individuals are capable of utilizing their brains with greater efficiency, optimizing their neural resources. If an individual is fortunate enough to possess this inherent cognitive advantage, they can playfully grasp intricate concepts and perceive them as inherently appealing. As we have already established, every brain delights in balancing on the precipice between simplicity and complexity. And yes, more brilliant brains, more highly refined intellects, tend to find greater aesthetic pleasure in more complex and nuanced intellectual challenges. Ramachandran notes that Albert Einstein possessed an unusually large angular gyrus, a specific region of the brain. This anatomical peculiarity, he speculates, likely enabled Einstein to integrate his computational and spatial reasoning abilities in such an extraordinary manner, a way that we, as mere mortals, can scarcely begin to imagine. For approximately a decade, Einstein dedicated himself to the arduous task of developing his monstrously complex theory of gravity. No one, absolutely no one, would embark on such a monumental intellectual undertaking without deriving profound pleasure, a deep intrinsic satisfaction from the very act of creation. As Frank Wilczek profoundly stated, if the laws were not beautiful, we would not have found them. And perhaps therein lies the very crux of the problem. Science, a discipline that ideally should be immune to the fickle influences of the human factor, has, up until now, often advanced precisely because of this very factor, this inherent human drive towards beauty and elegance. But what if this guiding principle, this aesthetic compass, ceases to be a reliable guide? What if it leads us astray? Hossenfelder, in her deeply contemplative work, writes that she already knows that the world embodies beautiful ideas. Therefore, her profound desire is to ascertain whether it also embodies ugly ones. It is entirely possible that humanity is destined to grasp only a multitude of small, localized truths, rather than one grand overarching truth about the universe. Perhaps the most fundamental reality is simply too chaotic, too intrinsically disordered, for our limited human minds to fully comprehend. Many of our uniquely human psychological traits, our distinctive cognitive abilities, undoubtedly emerged through the unconventional development of brain structures that originally evolved for entirely different, unrelated purposes. This phenomenon, known as exaptation, occurs frequently and consistently throughout the grand tapestry of evolution. Feathers, for instance, originally evolved from scales, their primary function not flight, but rather thermal insulation. The wings of bats and pterodactyls are exquisite modifications of anterior limbs, structures initially designed for terrestrial locomotion. Our own lungs, those vital organs of respiration, evolved from the swim bladders of fish, organs whose original function was solely to regulate buoyancy. Evolution has repeatedly discovered ingenious ways to radically repurpose the functions of many primate brain structures, giving rise to entirely novel and groundbreaking capabilities. Language, for example, proved to be such an extraordinarily powerful cognitive tool that the species it ultimately created, ourselves, surpasses its primate ancestors in terms of its impact and capabilities, much as life itself transcends the mere interplay of ordinary chemistry and physics. And our profound, almost innate love for engaging in scientific inquiry likely blossomed from a synergistic interplay of equally ancient, deeply rooted drives. We must therefore diligently strive to understand the genesis of these drives. We must comprehend our own cognitive biases, our often unconscious motivations, and the fundamental limitations inherent in our perceptual and conceptual frameworks if we are to truly progress. To fully comprehend the universe, we must, first and foremost, endeavour to comprehend ourselves. To truly understand physics, we must also possess a deep understanding of biology, psychology, and sociology. Quantum mechanics, for all its astonishing success and predictive power, operates with an almost unnerving effectiveness. Yet many physicists lament that it is inherently unintuitive, often defying common sense, and in a strange way perceived as ugly. Is this not perhaps because we, as a species, did not evolve to perceive the phenomena of the quantum world as inherently comprehensible or harmonious? Is the universe truly obligated, at all its various conceptual levels, to satisfy our deeply ingrained aesthetic demands, our human preferences for elegance and simplicity? The concept of naturalness, for example, has been employed as a guiding principle in the development of scientific theories since at least the 16th century. And yes, at times this principle has indeed proven to be remarkably successful, leading to profound insights. But at other times, it has demonstrably led astray. The same applies to the monumental proof of Fermat's last theorem by Andrew Wiles, a groundbreaking achievement first announced in 1993. The problem statement itself is astonishingly simple and elegant, a paragon of mathematical conciseness. Yet the proof itself is nothing short of an intellectual odyssey, a staggering testament to human ingenuity, an incredibly complex 129-page manuscript, utterly devoid of any inherent simplicity or brevity. In the vast history of science, it is far from difficult to unearth examples of theories and proofs that were undoubtedly beautiful, but ultimately incorrect. Conversely, there are numerous instances of theories that were complex and seemingly inelegant, yet profoundly correct. The connection between beauty and truth, it is entirely plausible, exists solely within the confines of our own minds, between our ears, a product of our unique cognitive architecture. Furthermore, expanding upon the idea of the subjective perception of beauty, it is worth noting that even many of the most brilliant and eminent scientists have, at times, held diametrically opposed views regarding which theories to label beautiful. The scientific work of Heisenberg, for example, did not, by any stretch of the imagination, consistently convey an impression of elegance to all his contemporaries. Erwin Schrödinger, another titan of quantum mechanics, famously remarked, "Of course, I knew about his theory. However, I was put off, if not repulsed, by the methods of transcendental algebra, which seemed to me very difficult, and by the lack of visualizability." Nor was Heisenberg particularly complimentary regarding Schrödinger's own ideas. In a letter to Wolfgang Pauli, Heisenberg wrote, "The more I reflect on the physical side of Schrödinger's theory, the more repulsive it seems to me. what Schrödinger writes about the visualizability of his theory is rubbish. Ultimately, both approaches, Heisenberg's abstract matrix mechanics and Schrödinger's more intuitive wave mechanics, became integral parts of a unified quantum theory. One might retrospectively argue that this very unification, this synthesis of disparate perspectives, was itself a form of profound beauty. However, let us consider another illuminating example. Neil Turok, a prominent cosmologist, dismisses the idea of the multiverse as fanciful, unnatural, untestable, and ultimately dangerous for science and society. From Turok's perspective, the multiverse hypothesis is a complete catastrophe. The American theoretical physicist Joseph Polchinski, grappling with the implications and plausibility of the multiverse, reportedly drove himself to such a state of intellectual distress that he sought psychiatric help. This is not a humorous exaggeration. Conversely, Leonard Susskind, another leading theoretical physicist, finds the notion that the universe might be far vaster, richer, and more diverse than we had ever conceived to be profoundly thrilling and inspiring. Bernard Carr posits that the very concept of the multiverse necessitates a new understanding of the nature of science itself, and it is therefore unsurprising that such a paradigm shift evokes intellectual discomfort. Max Tegmark asserts that opponents of the multiverse are emotionally prejudiced against the idea of displacing humanity from its central, privileged position in the cosmic narrative. And Atom Siegfried muses that the criticism levelled against the multiverse hypothesis is of the same ilk as that which compelled some 19th century scientists and philosophers to deny the very existence of atoms simply because they were unobservable. To definitively resolve this endless debate of subjective taste, what is truly needed are experiments. For nearly 2 millennia, 2,000 years stretching back to the time of Aristotle, people generally believed that heavier objects fell to the Earth faster than lighter ones. This conviction was based on an intensely intuitive, almost self-evident understanding. Some of you, even now, might find yourself surprised, perhaps wondering, wait, isn't that true? But then came Galileo. With a simple experiment, one that a 10-year-old schoolchild could easily replicate, he conclusively overturned 2,000 years of abstract wisdom that was founded upon our deeply ingrained internal preconceptions about order and natural behaviour. He demonstrated, with undeniable clarity, that objects of different weights fall at the same rate when other factors are accounted for, and so, it is precisely this absence of experimental data confirming supersymmetry that has led to a growing chorus of critics of this hypothesis, even among its former enthusiastic proponents. Mikhail Schiffman, a distinguished theorist, as early as October 2012, published a scathing critical article in which he explicitly declared that the theory of supersymmetry was unpromising, that it should be abandoned in favour of new ideas and for the sake of a new generation of theoretical physicists, lest they become a lost generation, trapped in a fruitless intellectual endeavour. Recall the words of George Ellis, the honorary professor from the University of Cape Town, from earlier in this monologue, regarding his assertion that a weakening of the requirement for testability would cast science back 1,000 years. He made this observation during an interview with Sabine Hossenfelder for her book, and during that same conversation, he articulated another thought that, even now, might stir indignation in a significant portion of those listening. He contends that contemporary scientists profoundly overestimate the boundaries of science and possess a strikingly poor understanding of both what science is capable of achieving and what it cannot. When Stephen Hawking, for instance, proclaims that God did not create the universe, is this a scientific assertion or a philosophical one? If it is truly a scientific claim, then where is the empirical evidence, the experimental data that supports such a definitive conclusion? When Victor Stenger pens a book asserting that science has disproven the existence of God, yet fails to describe any experimental apparatus within its pages that yielded such a result, a fundamental question arises: what precisely does Stenger mean by the term science in this context? When Lawrence Krauss, assuming the role of an ambassador for science, participates in debates concerning the existence or non-existence of God, and conducts them in such a manner that, by the end, everyone is metaphorically attempting to drink from an empty glass, ostensibly proving the existence of nothingness from his own book's arguments, how much scientific credibility does this add to his stature as a scholar? There is absolutely nothing inherently wrong with either affirming or denying the existence of God. Every individual, and specifically every scientist, is entitled to their own metaphysical position. But this, crucially, falls within the domain of philosophy, not science. If one wishes to argue for a philosophical position, then one requires rigorous logic and compelling arguments. And in the arena of attempts to scientifically prove or disprove the existence of God, there has been nothing genuinely new for 2.5 centuries since the time of David Hume, who brilliantly argued that science can neither prove nor disprove such an existence. Hume, observing the intellectual landscape, would likely be perplexed as to why his opponents continually resort to rhetorical devices rather than substantive arguments. All right, granted, I personally consider much of this rhetoric to be utter nonsense. But let us, for a moment, entertain the idea that these scientific debates about God serve as a kind of litmus test. They illustrate quite powerfully how the often disdainful attitude of many contemporary scientists towards philosophy inadvertently leads them down two problematic paths. On the one hand, they attempt to reinvent the wheel, unwittingly rediscovering philosophical concepts that have been explored for centuries. On the other hand, it leads them to an unconscious, unexamined faith in subjective criteria such as the concept of beauty in their scientific endeavours. George Ellis is one of the few individuals mentioned in Hossenfelder's book with whom she wholeheartedly agrees. She firmly believes that a concerted collaboration between physicists and robust, insightful philosophers, combined with a disciplined awareness among scientists of elementary cognitive biases, would undoubtedly propel scientific progress forward with a qualitative leap. By the way, the author of Lost in Math, Sabine Hossenfelder, maintains her own YouTube channel. So, if you're interested and possess a reasonable understanding of English, I extend a cordial invitation to explore her work. Richard Feynman, the celebrated physicist and Nobel laureate, articulated a fundamental principle that echoes through the halls of scientific inquiry. It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong. This unwavering commitment to empirical verification stands as the ultimate arbiter of scientific truth. And it is ultimately females who choose. Sexual selection has played a pivotal, indeed a fundamental role in the evolution of nearly all living organisms on Earth, and its influence is particularly pronounced in the development of Homo sapiens. The astonishingly rapid and dramatic expansion of the human brain is, to a significant extent, directly attributed to the relentless pressures of this very form of selection. It is widely hypothesized that the cognitive capacities of the human brain far exceed what would have been strictly necessary for mere survival within the savanna environments where our early ancestors roamed. Imagine, for a moment, our ancient ancestors, living 100,000 years ago. Their brains, it is conjectured, possessed the inherent capacity to grasp the complexities of quantum mechanics at a level comparable to our own. But for what evolutionary purpose? One compelling explanation posits that the very manifestation of our brain's extraordinary capabilities is, in essence, the equivalent of a human peacock's tail, an absurdly elaborate display of intellectual prowess. Recalling the intricate nests of the pufferfish, the bizarre architectural installations of the bowerbird, and the mesmerizing dances and songs of the birds of paradise, my mind immediately draws parallels to the archetypal narratives of human infatuation, the enduring allure of musicians, poets, and artists. Of course, in human societies, the dynamics of attraction are immensely more complex and multifaceted. However, the fundamental underlying principle, the core mechanism, is likely not as dissimilar as one might initially assume. It is conceivable that at a crucial juncture in our evolutionary history, the females of our ancestral species became so profoundly captivated by manifestations of intelligence, by the ability to solve complex problems, to communicate effectively, to create and innovate, that they were willing to undertake immense risks, even the life-threatening perils of childbirth, simply to ensure that their offspring inherited a similar intellectual capacity, both literally in terms of brain size and metaphorically in terms of cognitive ability, as the males by whom they were so deeply captivated. This process, while certainly a gradual one, was nevertheless remarkably swift by evolutionary standards, and it is precisely this rapid, almost explosive expansion of cranial capacity that makes human childbirth such a challenging and often dangerous endeavour, hardly an elegant solution from nature's design perspective. Indeed, the maintenance of such large human brains entails significant biological costs. I anticipate potential objections to this line of reasoning, so let me clarify. A strong belief is deeply ingrained in our society that it is primarily men who choose women. However, this perception is in fact not entirely accurate. If you find yourself puzzled as to why, in the natural world, it is typically females who make the choices rather than males, the answer is, from a biological standpoint, quite straightforward. For a female, the process of reproduction is, firstly, inherently dangerous, and secondly, significantly more resource-intensive. The number of offspring that a single female can produce is severely limited, in stark contrast to a male who, given the opportunity, could potentially father an entire division of descendants. Therefore, even in populations where the ratio of men to women is roughly equal, an incomparably greater number of males, on average, competes for the attention and reproductive opportunities of a single female compared to the number of females vying for a single male. Men propose but women choose, and those males who are chosen by a significant number of females are the ones whose traits are perpetuated. The others, for the most part, are evolutionarily culled. This phenomenon is further, and partially, corroborated by the striking observation that humans have a significantly greater number of female ancestors than male ancestors. The evolutionary psychologist Roy Baumeister, in his thought-provoking book Is There Anything Good About Men?, notes that research consistently indicates that humans possess twice as many female ancestors as male ancestors. This implies that a vast proportion of men who have ever lived on this planet simply failed to leave any descendants. You might reasonably inquire, how is such a stark disparity possible, especially if the ratio of men to women is approximately equal? The explanation lies in this fundamental dynamic. On average, and I emphasize on average, almost every adult woman in history has had at least one child. However, while some men fathered children with multiple women, a substantial portion of men left no offspring whatsoever. While the precise mathematical details are undoubtedly more complex, this rough illustration vividly demonstrates how such a disproportionate ancestral lineage could have arisen. In a broad sense, it can be argued that evolution conducts its experiments primarily on males, because in the event of a successful mutation or advantageous trait, a single male can potentially produce a vast number of offspring, thereby rapidly disseminating that trait throughout the population. The reverse, however, is not true. And yes, this, as I asserted, is largely the very mechanism through which we evolved our almost magical intellectual capabilities. The fact that, in nature, females choose is indeed a truth, but it is nevertheless a somewhat loudly stated generalization. This is because it is not, of course, a conscious, rationalized process. Consider the female pufferfish or the bowerbird. Something intrinsic within them simply resonates with what they perceive. What is this something, and why does it operate in this manner? That truly is the fascinating question. And humans, too, significantly overstate the conscious component in their own lives. Women, for example, often do not precisely know why they fall in love. It is a process that largely transcends their conscious control. If my male audience currently entertains the notion that every woman is searching for a partner from a world of platonic ideals, a perfect male who simply does not exist in our imperfect sublunary reality, then what of this even more intriguing example of enigmatic aesthetic preferences? Consider the astonishing observation that female guppy fish consistently prefer males who are painted blue, despite the fact that guppies themselves are not naturally blue. This appears to be a peculiar, almost whimsical quirk of their neural wiring, an arbitrary aesthetic preference. If by some improbable chance a spontaneous mutation were to occur, resulting in a single blue guppy, one could confidently predict over the course of the next several millennia the emergence of a new race, of guppies that would evolve to possess an increasingly vivid, almost uselessly intense blue coloration. Females transmit to their offspring not only the specific qualities that attracted them to a partner, but also, crucially, their innate preference for those very qualities. Ultimately, the final arbiter, the supreme examiner, is of course reality itself and the relentless pressures of natural selection. Through maladaptive sexual selection, a species can, astonishingly, even face extinction. This, for instance, is believed to have been the fate of the saber-toothed tiger. During the Ice Age, they were deprived of their customary prey, large mammals, including mammoths. Their absurdly oversized canine teeth, which according to one theory were purely decorative and existed solely to attract females, rendered them incapable of effectively hunting smaller game. This critical inability to adapt to changing food sources ultimately led to their gradual but inevitable demise. However, if a species manages to survive for an extended period, it strongly suggests that this species has, through its adaptations and behaviors, grasped something fundamentally important about reality, something that enables it to continue to exist. Much like our architectural structures that do not collapse because they are founded upon deep, robust theoretical principles, so too are we. We are, in essence, an embodied theory of the world, a living, breathing hypothesis that to some degree accurately conforms to the fundamental laws by which the world operates. This embodied theory, however, is far from complete. If you were to represent a complete unified theory of the world, you would be capable of living in any conceivable environment, and indeed, you might even be able to live forever. It is possible that we are currently bogged down in the foundations of physics, having reached the ultimate limits of what the human mind is, in principle, capable of comprehending. We do not know the precise depth to which our genetic inheritance allows us to penetrate the very essence of the cosmos. Yet, considering that Homo sapiens is arguably the most successful species on the planet, a testament to the selective nature of our women, a certain degree of understanding is undeniably within our grasp. As David Hume, the brilliant Scottish philosopher, wisely posited, the cause or causes of order in the universe probably bear some remote analogy to human intelligence. You have assembled the puzzle. Thank you for your viewership, and my deepest gratitude to those who provide their continued support.